And the second part, so if you missed the first part, no problem. I'm quite sure it will be very interesting. Thank you.
Okay. You can. We don't have.
Yeah, let's see.
Ah,
oh, yeah.
You found it.
Okay.
Okay.
There you go.
Thank you so much for the introduction. I'm very happy to be here to speak here, to talk to you about what we have done recently on the simulation of plasma-assisted combustion. So I must first tell you that I'm not a plasma physicist. So we just came from a combustion background, trying to incorporate some plasma physics, what we understood of it, into our simulation tools and modeling tools to.
The audience is online.
Yeah.
It's not seeing you, but only the picture of me.
Ah. This is due to the.
Oh, yeah. I think I need to switch the camera on.
Yes, it's camera.
Let's see here.
Yeah.
Yeah, maybe it's better now.
But then maybe we need to do something like that.
Yeah.
How is it now?
We should be able to see like a small picture, no? Then no. Oh no, this is not. Let me see. Oh yeah, here. I see. There you go.
Ah yes. Yeah.
Okay. It should be okay.
Just start from scratch.
Okay. Yeah. Yeah. Everybody. Ah yes, you can see me now. Good. Okay, so I start again. So I was saying that I was very happy to be here to present you what we have done recently on plasma-assisted combustion. I was mentioning also that we are not plasma physicists. We come from combustion, mechanical engineering even. So we try to incorporate some plasma physics into our simulation tools to work on plasma-assisted combustion. So we had, I'm working on this topic with a colleague, Olivier Vermorel, and two PhD students who, in fact, are not anymore PhD students. They have defended, but this is their work. So I will start with a brief introduction, a bit of context. If I can move to the next slide. No, doesn't want to.
Yeah, let me see.
Yeah, I need to.
Yeah.
So a bit of context. So we are, of course, in the context of the climate, environment. We we know that society is really demanding about renewable energy, but we have a problem, well-known problem of intermittency and distribution of this energy. So one possibility to solve this problem is to use gas turbines that are usually still now fed with fossil fuel, fossil gas. But we want to use this, taking the energy from this renewable energy to store energy in the chemical state into, for example, biomethane, and feed our gas turbines here to produce and distribute energy where it is needed. So, but of course, in that step here, we need also to reduce the CO2 emissions. This is so we don't want to reproduce the CO2 emissions that we have not produced in the first step. So to do that, we have to go for new technology, even for these gas turbines. One is new fuels, of course, hydrogen, but also other types of fuels. But a very important aspect is to go lean or ultra lean combustion. So this has a direct effect on the CO2 production. And this is what we are interested in this topic. Why? Because lean or ultra lean combustion leads to a kind of unstable combustion. It can lead to misfiring, extinction or blow up, or you can also have all kinds of instabilities. So this is where okay, this is where, how can I do that? Yeah, plasma-assisted combustion will help us, because I hope is that by adding some energy into a plasma well located somewhere in the burner, we will solve these problems of ignition and flame stabilization. So just as an example, we know that this works. We know that from experiments, you have a nice experiment by Bernard in Coast, where you see here a small flame. This is typical flame that we have in gas turbines. The blue part is the flame, and you see the purple part is the plasma. It's an arc discharge. And you have on the right side here some recordings of the velocity, and below you have the spectral density of the signal. In black, you have the recording without the plasma actuation, and in red, you have with the plasma actuation. And you can see very well that the impact of plasma is really to stabilize the flame. This is very clear here, and this is well now established that this plasma discharge here really helps in stabilizing the flame. So the question now is how do we obtain what is this result coming from? We don't. This is a question we want to solve because the experiment does not really give us this type of answer. So let me go to the next slide. So now talking about plasma discharges, we have a whole range of plasma discharges. So I will be talking here on your cold plasma, not by contrast with hot plasma, which are fusion plasma that you find in nuclear processes and so on. So it's cold plasma, which means that we stay with reasonably low temperatures, not more than a few 10,000, right? This is considered cold for a plasma. You see in this picture, in this diagram here, and you have on the axis of the electron number density and the electron temperature on the next. We have a cool, very wide topology of all possible discharges. Flames, of course, are the very low left bottom corner, very low electron number density and electron temperature at the same temperature as the gas, quite low. But then if you increase the electron temperature, so you go to non-equilibrium plasma, you go to the higher electron number density, you go with ionized flow, and you have all kinds of discharges possible in this diagram here, from spark to corona or simple glow that you find in the neon light also. This kind of thing. These are all well known. And a first distinction that we can make in this cold plasma is below here. You have the equilibrium case, what we call thermal plasma. Why thermal? Because you see the electron temperature and the gas temperature are the same. And the gas heats a lot with this thermal plasma, right? This is gas really reaches high temperature levels. This is what you find in plasma torches, for example, that are maybe used in cutting to cut some material, things like that, or in spark plugs that are standard ignition devices that you find in engine. We will be talking today about the other kind, which is non-equilibrium plasma. In that case, we see that the electron temperature is much different from the gas temperature. The gas temperature stays quite low. There is no real increase, direct increase of the gas temperature by this plasma, while the electron temperature goes very high. And this type of non-equilibrium plasma is reached when you do, one way to reach it is to do this nanosecond repetitive burst discharge, which means that as sketched here, these are discharges that are obtained when you apply high voltage pulse, but for a very short time. So the plasma does not have time to go to equilibrium, right? But typically the duration is a few tens of nanoseconds, 10, 20 nanoseconds, and the frequency between 10 and 100 kilohertz. Even in that case, for these unearthly discharges, you have various regimes depending on the maximum voltage. You have corona, glow, or spark. And all these type of unearthly discharges will be useful for us. So this is what we will be focusing on today. So now if I go to the next slide, so what is the impact of our discharges on our combustion system, our gas mixture? In fact, we have, you can see in this right sketch here, we have three types of interaction of this plasma with our mixture. You have a direct thermal effect, like a direct heating of the gas by the plasma. Then you have also another important effect, which is the kinetic aspect. I'll come back in a minute. So the plasma, when it is generated, contains a lot of radicals that may be very helpful for the combustion. And we also have some transport effects to typically iron ring, for example. So in the NRP discharge with combustion, the most important part that we are interested in are in the thermal and kinetic aspect, but the kinetic aspect is really the key part. And this is, you have here on the left side, some sketches on how the plasma chemistry interacts with the combustion chemistry. In fact, you see all these atomic radicals and electrons introduced in the overall, for example, methane oxidation scheme. So these are chemical reactions in a way that will add to the standard combustion chemistry that we already have in our systems. So now what is a discharge? So we want to simulate a discharge, right? So we have two types of discharge, what we call streamers. In fact, when you have an anode and a cathode, so you have the electric field from the anode to the cathode, and then you have two types of streamers. One kind of streamer, what we call positive streamer, from the anode to the cathode, where you see that this streamer, the head of the streamer is contains a lot of ions, a positive charge. Then if you look at the middle sketch here, you see the shape of the various fields, electron field, state charge, and electron density through this red line here. So you see that these ionized particles, they create a space charge. So they then induce an electric field that will allow electrons to ionize the air that is just upstream of the streamer, and this is how the streamer will propagate. This is a kind of positive streamer. In the kind of negative streamer, it's the contrary. So the streamer starts from the cathode and then propagates to the anode. The head of the streamer is has an excess of negative charge of electrons, and then these electrons will directly ionize the air that is outside and propagate in that way. So in this case, the negative streamer propagation is much more simple and direct than the positive streamer propagation, because here the streamer can propagate only if there is sufficient electrons around the head of the streamer to allow the ionization. And it goes through this interaction with the electric field produced by the ions themselves. So we need what we want is to reproduce this type of phenomena. But to do that, so this is just the part of the, let's say, streamer shape. But as I said, an important part that we need to see is the plasma chemistry. In fact, as I said already, the major effect of plasma on our combustion will be the plasma chemistry. So we need to go through that. So how does it work? It's just that the electromagnetic energy, it transfers the electron energy, and the electron energy then through reacting process collisions will transfer the energy to the gas in various energy channels. So typically, the energy channels that are identified for the transfer from the electron energy to the gas are the electronic excitation of the molecules, vibrational excitation, ionization, and dissociation. You have an example here on this sketch, depending on the reduced electric field. So the electric field divided by the number density of the particle. You see the energy fraction in each channel for oxygen and nitrogen, depending again on this reduced electric field. So we have a split that changes a lot depending on these two quantities. But the interval, the range we are interested in is just sketched here in red. It's between 100 and 400,000. And in that region, you can see that we have two peaks. One peak of nitrogen excitation with the black circle with a dashed line, and one peak corresponding to oxygen dissociation, which are the purple line. And also we can see that after 100,000, the relaxation of the vibrational energy of nitrogen decreases a lot, but it's still there. So just to this is just to identify or indicate to you what are the major processes when you discharge in air. This will be mostly these. So nitrogen excitation, oxygen dissociation, and nitrogen vibrational relaxation. This is for discharge in air, of course. This will be our major processes. So, so that's the second well-known feature of this plasma discharge is that because of the different channels, in fact, we can distinguish all, we can categorize all these processes into processes, major processes, fast processes and slow processes. So the fast processes correspond most with the electronic excitation of the molecule with through the collision with the electron, as shown here. So this is very fast, and then the excited nitrogen will be transferring its energy through other reactions with, for example, oxygen into vibration, but also other radicals. And this process will also release some heat directly. So this will be all these represent different energy transfer channels. And this is very fast. On the other side, we have slow processes, which are a direct excited vibrational state of nitrogen. And this vibrational state will relax its energy in a much more slower process through, for example, collisions with atomic oxygen. And this will release a lot of heat, but on a much longer time range, much later. So we have these two kinds of processes, fast and slower ones, that we will need to describe. Then we also have to describe the non-equilibrium state of these electrons. As I already said, in this type of discharge, we have electron temperature much higher than gas temperature. So they are not in equilibrium. And so for non-equilibrium particles, we need to solve the electron distribution function, which is a distribution equation, as a population distribution equation, as we know for any particle population. And then I will not go through the math, it's a bit difficult, but to solve this complex equation, there are some assumptions that are applied and approximations that are made. And the first one is that this Fe, this electron distribution, is first expanded in a two-term approximation in a F0 and F1. And then F0, that is the only one that is kept, is again is manipulated and to be related to another capital F0, for which we have this equation here, which is called the electron energy distribution function, right? So at the end, this is what is solved, and this is solved with dedicated solvers, as I will just show now. So at the end, we have something we have to derive an algorithm and code to solve both combustion and plasma chemistry. So combustion chemistry can be computed with your favorite chemical code like Cantera. That's the one that we use. So we just put in Cantera, if we are doing methane air, so we just include our favorite methane air combustion chemistry mechanism there. And we add also the chemical mechanisms that are that include all the processes that have been identified to be important. So we have here examples, for example, for the N2 excitation and quenching. But all the other are there. They are in the form of standard reaction as would be for the combustion and with reaction rates and so on. The reaction rates are taken from cross-section databases that are available for most of these molecules. But on the other side, we have to include to solve this electron, this EEDF equation, electron energy distribution function, and this is done with, as I was saying in the previous slide, with dedicated solver. So we used one famous one that is called Bolos that has been developed by Aguilar, and this just solves this equation for you. So we just took it and coupled it to Cantera. This solver after solving the EDF equation gives you the electron temperature and the reaction rates that involve the electrons. Right? So at the end, we have a complete set of solvers to solve on one side combustion and plasma chemistry, and on the other side the evolution of the electron population that is out of equilibrium. Right? So we call that PLACEM. It's just a name. It's just the combination. It's just the integration of Bolos into Cantera. Then with that, so having that, the first step was to validate this plasma chemistry. So this is what we did. So there are some experiments that you can find in the literature. So one is the one of Prosperoids. It's a nice one because it has a lot of measurements. So the Prosperoid experiment is from École Centrale in Paris. It's simply an electrode on a transfer, as you can see here, that are put in a heated flow, and the discharge are applied at a frequency, I think, of 10 kHz. And after some time, a stationary state is reached, and measurements are made. So the stationary state is indicated here with this arrow. So we have an evaluation of the state in the space between the two tips of the electrodes that have been evaluated by the people who have done the experiment. So we have a composition here that is again the stationary state of composition that is obtained after multiple sparkings, multiple discharging. On the right, you have an illustration of the typical pulse when it is applied. So you have the voltage, the reduced electric field, and the current. And you see typically what is just remarkable here is the time of the pulse. Right? It's very short, between 10 and 20 nanoseconds, no more than that. And then, as I was saying, many quantities were measured just at the center between the two electrodes, temperature and various molecules and radicals. So we took these initial conditions and we made the simulation of one discharge, and then we could compare with the experimental result. So you have here the atomic oxygen as a function of time. Then you have the temperature, and then the excited nitrogen density. So we have two states of nitrogen that have been measured here. So first of all, we see that the symbol, the status of the experiment, the solid line is this work, our work, and the dashed lines are previous correspond to previous work of Prof in 2013. So you can see that we correctly predict the atomic oxygen. We also correctly predict the fast heating of the gas. So the part is in this zone, right, below before the 25 nanoseconds. So we have the very fast dissociation of oxygen with the associated fast heating, again associated to dissociation of oxygen here and some of quenching of the excited nitrogen. And then we have a bit less, much less rapid increase of temperature associated to the quenching of other excited species afterwards. And again, we have also a good comparison between experiment and simulation of the N2 excited state. So with this validation, we can see that the model, the plasma chemistry that we have included correctly reproduces the behavior of the discharge in air. So now if I go further, we can analyze a bit more this discharge and evaluate the relative importance of each channel of energy transfer between the plasma and the gas. So you see that a lot of things occur during the pulse, at the very short times here. But at the end, we see a large part from to the chemical channel, and then followed by the direct heat. Then we see also the important part of vibration energy. And we also see that the ionization excitation goes rapidly to zero, because these are associated to very fast processes, as I was already explaining. And so they are very important during the pulse, but they rapidly go to zero. So if in quantitatively speaking, if we compared our sharing of energy with other previous results, so we have the two first line corresponds to this one at 25 nanoseconds, just at the end of the pulse, and then later on, 100 nanoseconds. Then there was an evaluation also proposed by the people who did the experiment, and then two simulation cases. So the one of Prof that I already mentioned, and another by Castella, who used a simple model. So they used they intuitively attributed some constant share of this energy distribution in their model. I will come back also to that later, but what we can see is that with our approach, so we have all channels evaluation, but we see for the in the green column, so if you compare with other, at the end of the pulse, we are quite close to the other evaluations, both for chemistry and heat, and we see a difference or if the sharing of the vibrational energy that we find much lower than in the Castella model. Again, I repeat, in the Castella model, this 45% of vibrational energy was just a guess, or from experience, it was not based on detailed chemical simulation. What we observed is that the discharge in air is that the major species that are produced, and this is important for combustion, are the O oxygen atom, N atom, and NO molecules. These are the three that will be directly interacting with our combustion scheme. So this means that the processes that we will need to include in our chemistry are these. So oxygen dissociation, nitrogen dissociation, and this other third process that creates NO. Then, okay, this is discharge in air. So discharge in air are very widely studied. If you go to the plasma literature, you will see most work related to discharge in air, but we are doing combustion, so we do not have air. We have air with fuel and we also have burn gas. So the second step was to try to model a discharge in a fuel-air mixture. So this was done with methane. So we just did the same type of simulation, but now including methane. So we took a plasma mechanism for methane air from the literature, and we identified the most important processes that are shown here in the right side. So the direct interaction of methane with electrons, the interaction of methane with excited nitrogen, and the interaction of methane with atomic oxygen. So these processes are important and really add to the combustion chemistry. And we could also validate this chemistry and the result with two experiments. So one was in a low energy discharge, that the authors did both air and methane air mixtures. So you see here, for example, the fraction of the O atom comparison with our simulations and experiments. So you have our simulations were performed with two different methane air combustion chemistries, the one the GRR and the one from Cuenot. We also compare with another simulation from the people who did the experiment in the dotted line and the experiment. So you can see that our results agree well with the previous simulations and also with the data. So this is the first validation, and the second validation was the plasma-assisted ignition. And here you show the temperature time evolution. So we compare with another simulation also done by the people who did the experiment, and you can see that we follow well the results. The ignition time that we find is about 3-4 microseconds, while the experimental ignition time was 2 microseconds. So again, here we consider that our methane air plasma combustion mechanism can be considered validated. So to conclude on the plasma chemistry part, as I was saying, we also extended that to burn gases. So in burn gases, you need now to also take into account CO2 and H2O. This is what how we defined our burn gases. I think this involves other processes, other reactions with electrons. And then when you do that, you end up with a very, very long, very large size mechanism. So the next step was to reduce, as we do usually for chemistry, for combustion. So we did that with our own code, which is called Arcane, using a DRG-EP method. So interestingly, you cannot use quasi-steady state approximation for plasma species because they are never in quasi-steady state, so it doesn't work. The only method that you can apply is DRG-EP. But with that, we could still reduce the mechanism and live with 44 species and 410 reactions, which is still a lot, but is much less than the initial scheme, right? And with that, we could make first multidimensional simulations that I will show now. So to do multidimensional simulation, we end up with a set of equations. So you recognize the Navier-Stokes equations with the chemical system for the species that come from the chemistry. Then you have the momentum equation that is unchanged, and you have the energy equation where you have the contribution of the chemistry and the contribution of the other from the vibrational energy. So the blue square corresponds to the heat coming from the chemistry, including the plasma combustion, right? It's not only the combustion chemistry, it's also the plasma chemistry that, as I explained, really releases directly heat to the system. This is for the fast processes, remember well. Now, for the slow processes, this cannot be put into the form of reactions. So for that, you need an additional equation for the vibrational energy that you will compute in the form of a transport equation, where you see here the plasma contribution of vibrational energy, and that is then producing, let's say, this term here, that is linked to the way this energy is then transferred to the gas. Okay, and in this model, in our that we took from the literature, this transfer to the gas is proportional to the vibrational energy and the relaxation time that comes from databases. And this R dot VT, right, is added to the energy equation. So again, the vibrational energy receives energy from plasma and then gives it to the gas through this term, right? And finally, we have the transfer equation for the charged species. For the charged species, it's common to use the drift diffusion approximation, which means that the inertia forces can be considered negligible. And then you also have this reaction rates, which have come from Bolsic Plus, which is the library that makes the same job as Bolos in the Cantillon, right? So this is for electrons and those other charge species. And finally, because we have charge species, we have an electric field that we need to solve, because this electric field is a driving motion force for all the charge species. So we need to solve for the electric field through this Poisson equation, where here is the potential, electric potential, and that is related to the charge field, depending on the concentration of all charge species that you have in your. So this Poisson equation is a well-known equation in CFD. For example, it's the same equation that you find in incompressible flows for the pressure. So you put that in a linear, you discretize that in a linear system, and you solve it with your favorite library for linear systems, and we use PETC to solve that. So with that, with this set of equations, we are now able to compute a discharge, plasma ignition, plasma assisted ignition in a metaneration. So this is the case that we applied it to. So it's a methanol mixture at the equivalent ratio of 0.5. It's usually at 600 Kelvin at atmospheric pressure. You see here you have the two electrodes. This is the computational domain with the two electrodes, and then we have the shape for, oops, sorry, for that. And so, yeah, positive symmetry. And we did several cases for this plasma-assisted combustion. First, we did one case with one single pulse, one single discharge, right, in the domain, with an energy that was varied between 400 and 600 microjoules, only one pulse, and plasma on. Then to see the impact of plasma compared to a standard ignition with a heat deposit, that would a spark plug lead to, we made also a simulation with simple heat deposition, so without plasma, and same time, same order of magnitude of deposited energy. And finally, to see the impact of multiple pulses, which is the case of nano repetitive pulse discharge, we did multiple pulses with reduced energy. So each pulse has a much lower energy. And we have the various frequencies of, we tested various frequencies of multiple cases. So let's start with the results on the single pulse discharge. This is the, okay. Yeah, so this is how the discharge works. So you see the two streamers, one positive, one negative, coming from the two electrodes. This is the number density field of electrons, and this is really the discharge phase of the case. And then if we look at what we have in terms of energy density, you can see that at 3 nanoseconds, in fact, we have not deposited any energy yet. The energy is deposited after some time, after 14, but at about 14.7 nanoseconds, we have established a kind of channel where the energy, the plasma has deposited energy into the system. And so this energy density mark here is what we use to start our energy deposition simulation. When we when the case where we have no plasma, but just deposited energy, we use this shape, this channel shape, by a simple proportionality between the electron, the energy density, and the heat, to have something comparable between the discharge and the energy deposition. So now, if we compare all these cases, so we have here a single pulse at 500 microjoules, energy deposition at 500 microjoules, and energy deposition at 600 microjoules. 500 microjoules was the amount of energy that was found the minimum to for a successful ignition. And so I will show you the movie. if it wants to work. Too bad. Okay. Is that all for all? Okay, yeah.
I need to advance to the screen. Yeah.
Ah, sorry.
Yeah.
I was
Do
not
you want to
clicking.
click out of it?
Yeah, yeah. I will try.
Oops.
I think I will find.
Okay.
Thank you. Okay, so if we go back here, so you see the two streamers producing two hot kernels close to the tips of the electrode, right? These are just, we are just at 100 microseconds here, so we are not looking yet at the ignition of the gas phase, it's just the beginning. If we compare to the energy deposition here, okay, thank you. You see, in fact, we also have a start of kernels close to the tip of the electrodes, but they rapidly fade out, and this leads to just quenching. So it means that at the same energy deposition, the plasma is able to establish a hot kernel, while the simple energy deposition is not. And so for energy deposition to have successful ignition, we need to increase a bit the energy deposited, and then we end up with something that also has the two kernels moving. So you see in that case that we have a much higher kernel on the side of the anode compared to the more symmetric distribution of temperature, field of temperature in the case of the single pulse. So the first conclusion is that, okay, the plasma really seems to have an effect and a real impact compared to the simple energy deposition. And the explanation is from plasma chemistry. Okay. I have to go back. Ah, yes, it's here. Okay. Yeah. So now, we continue the simulation, so only for the successful ignition, and we look again the two cases of the single pulse and the hydrogen deposition. So the single pulse, you see, really is able to ignite the mixture with a very symmetrical shape development of the kernel. If we look at the energy deposition, we also have ignition here, but with something again that is much less symmetric. What we can see again here that the discharge really has an ignition that is much faster. If we look at the size of the kernel, it's at the same time. The size is much larger in the single pulse case plasma discharge. So yeah, okay. Now, next step was to go to multiple pulse. So we have a first pulse here established, and then so it's only 50 microjoules, so it does not ignite already, yeah. And then we repeated this process at various frequencies. You have here the pulse 2 and 5 for a case at 10 kilohertz and a case at 50 kilohertz. What you can see is that in both cases, we have a kind of a concentration of the electron number density, because thanks to these repeated pulses, then the electron number density piles up, builds up one pulse on the other, and we end up with something that is much more intense here and much more contracted. So we see that having repeated pulse discharges really builds up a lot this plasma intensity, which will be helpful for ignition. If we go to the ignition phase now, here you have on top a case of, you have here a case at 50 kilohertz. On top you have the discharge phase, and on the bottom we will see the ignition phase, so continuing of the discharge phase. In that case, we have 7 pulses, right? So let me show you so this is temperature field. So you see the different pulses. And you see how the temperature locally increases. And at the end, we have a nice channel of hot gases inside between the two electrodes. If we look at the heat release rate here, yes, we also see that, of course, intermittently we see something, but we just start to ignite something, to ignite a front here. And now if we continue, so after we stop the process and we see if the mixture ignites. So you have here the development of the kernel. So of course, as expected, in that case, the kernel expands and we have a successful ignition. And you can also see that under heat release rate feed, we have a flame front expanding and we have a successful ignition. Okay, let's go to the next. Yeah. So if we look at what happens in the center of between the location just between the two electrodes here, we try to see how many pulses we need to ensure ignition. So you see in that case, we have the black line is with the plasma on, and the gray lines are with plasma off, right? So, for example, in that case, we did 3 pulses, and then we stopped the pulses, right? And you see that before, below 6 pulses, you'd never ignite, because even after 5 pulses, you go very high in temperature, but then it decreases. So we are not successful to ignite, whereas starting at 6 pulses and higher, we ignite even after stopping the discharges. And yeah. And if you look at the temperature at this location, so outside the plasma channel, you see the same thing, that after 6 discharges, then you have a nice temperature rise up to ignition. So we repeated this exercise for various frequencies between 10 and 100 kilohertz, and this is what we obtained. So you have here the result in a diagram of ignition delay time as a function of the number of pulses for various frequencies. So in red, you have the energy discharge that is minimum to ignite in energy deposition without plasma. In blue, you have the minimum energy that was found to ignite for a single pulse. And then in black, you have the minimum energy that was found for multiple pulses. So what do we see here? We see that below 20 kilohertz, ignition never occurs. Remember that we have only 50 microjoules for each pulse. So it means that in that case, you do not deposit sufficient energy sufficiently fast to allow ignition. Then if you continue, between 20 and 25 kilohertz, you see that single pulse is more efficient than multiple pulse, because you see that the single pulse minimum energy is lower than the energy that is used for this for ignition, to have a successful ignition at these frequencies. So still you ignite, but you do not ignite sufficiently frequently to have something more efficient than one single pulse with more energy. If you continue, then you go above 25 kilohertz, and then in that case, you see that multi-pulse is more efficient. You need less total energy than the single pulse energy to a successful ignition. And finally, if you go further, then the minimum ignition energy does not evolve anymore, but you still have a faster ignition as long as you add number. Okay, so with that, we have a good view of how the plasma acts on the combustion on the mixture, but these simulations that I've just shown are only 0D, and even in only 0D, they're very testy. So there's no way we can do that in a, no, they were multi-dimensional, sorry, but in a very small domain. It was just between two electrodes. If we want to apply plasma in a real 3D burner, there is no way that we can use this model. So we went a step further and we developed a model which is a kind of phenomenological model, right? It's not a theoretical model, to reproduce these two effects, the ultra-fast effects from the radical to gas heating and the slower gas heating due to the vibrational energy relaxation. And how do we do that? So we take again our distribution of the energy of the plasma into different channels. And then we define the fractions, okay? We say that one fraction is going through the chemical channel, one fraction is going to the heating channel, and one from the vibrational channel. And we just pre-calculate these fractions, right? So we take we do a chemistry simulation corresponding to the case we are studying, and we pre-calculate this fraction, and we just input that into the code. So we do not calculate them online on the fly inside the CFD simulation. Again, we pre-calculate that. This is not a new idea. This is the same idea as in the model of Castella that I was just speaking about a few slides ago. They did the same as that, but they did not pre-calculated the fractions. They just guessed values from their observations. So the advantage is that now we have a tool to evaluate these quantities. So if I take the case of this charge in air, this is what you get. So you pre-calculate the quantity, these fractions. You have here the results in a table compared to other evaluations made by others. You see that we are more or less in the same range, but slightly different. And we have different processes. We have identified the processes, the chemical processes with our chemical tool. So each processes, like for example, N2 quenching has its own alpha, right? So we can really determine each fraction of energy through each process. You have the result here in terms of NO and temperature. In the comparison with experiment with the symbol, the model of Castella in blue, and our model is called Pacman in red. And you see that we will reproduce the experimental results and better, at least for NO, than the Castella model. If we also apply that to plasma assisted ignition case, the same that I just described before, for which we had a lot of measurements at the center of the configuration between the electrodes. So you recognize one successful ignition event. So we did a lot of different cases. With EN is reduced electric field. So we change the reduced electric field and the equivalence ratio. And you have 7 processes that have been identified with the help of our chemical tool. And they have the alpha heat and alpha dip. I will show this case, 200 correction, reduced electrical field and C equals 0.8. But what I wanted to show you here is that in fact there is no clear trend of these coefficients with these 2 parameters, reduced electric field and equivalence ratio. It was not possible to find a kind of trend. So these are what we found, but we cannot do better than that. We don't know how to model these alpha, for example. We just have to compute them and put that into tables. But with that, we could verify that we recover the right result. So you have here the comparison on the center line between the 2 electrode tips of the temperature here. So we sign, okay. You have the comparison again of the model in red, the Pacman model, our model. In blue, you have the Castella model. And in black, you have the reference simulation, coupled simulation that we could pay for this case, right? And you see that our model really follows very, very well the detailed simulation, much better than the Castella model. Of course, we have more tuned parameters, as that's normal. And in particular, we see that you see here the 2 traits of the 2 kernels that we saw during the simulation. You see that in the Castella model, the merging of these 2 kernels is a bit slower. Another comparison is here. You see here at the center, temporal revolution at the center. For example, CH3 radical, you see many differences in the two models, especially for this quantity. You see here the Castellar model for NO, for example, predicts no NO because this was not taken into account in the model. So we can say from that we have now a good model and validated model and improved compared to the literature. So if I go fast, I will just show you to finish first attempt to apply plasma-assisted combustion, so plasma discharges. To this case, this is a short flame. It's very similar to, in a very similar configuration to the one I showed at the very beginning in the picture. This is without plasma. You see this flame being very unstable. It's really is very intermittent at the basis. Various cases were tested, so we picked the C3 case, and we applied the discharge with the pathline model that I just described to this flame. So the tricky part is that this plasma discharge is between the black body here and the outside cylinder, and it rotates because it's a swirling flow, so the discharge rotates with the flow. And so we had to also make this rotating motion of the discharge into the simulation. But you can see here that when you have the resisting flame, I hope you can see this plasma discharge trace. And with that, we could demonstrate that the flame stabilizes very well. So this is about the end of the story of today. So what I can say is that we have a tool now to include and analyze, to build and analyze plasma-assisted combustion chemistry, including all radicals, all important processes. We can do that for burnt gases, and we are currently working on hydrogen because this is, as you all know, a very relevant topic now. We have the tool to reduce the obtained plasma chemistry combustion to make it more handleable in simulation. We have a tool to perform we call that detailed, or at least coupled plasma combustion simulations, including this very detailed chemistry and including the electron and the associated electricity field. And finally, we have a model to apply plasma discharges to 3D real burners of larger size, for which we could not do these coupled plasma combustion simulations. And a final slide is about one particular point that has been kept us busy for a while, which is how to accelerate these simulations, not chemistry, not all that, because what is the most demanding, surprisingly, or maybe not surprisingly, I don't know, it is linear system of the Poisson equation. Okay, this is crazy because, well, from mechanical engineering and turbulence field, I thought that the nonlinearity of turbulence and chemistry was the worst, but no, it's simple linear systems that are the worst in terms of CPU. If I just use a standard method for linear system resolution, I spent more than half of the CPU on that. So I decided that it was not possible and tried to find another way. And a good candidate for that is neural networks, right? Because we have a linear system, so linear system is good for networks, for deep learning, and so we try to apply that to train a convolutional network onto a random fields database, apply that to a discharge. And you have a result here. You compare here the results of, you have the electron density and the electric field from the network and from the standard iterative method. And you see that the quality is very good. So the question is now, and it's much faster. Huh? The CNN, you get the results in 100 times faster than with the iterative method. Now the question is this accuracy sufficient? or not? And how now do we couple that to the CFD code? One difficulty is that this works only for structured grids. Neural networks, standard neural networks only work for structured grids. So we are now currently working on graph networks to handle unstructured grids with more complex geometry. But this is very, very helpful. And I think that it will help us a lot also. And with that, I think I have passed over my time. So that will end now.
Thank you very much. I think the audience has made a big effort, and you have also made a big effort to inform us about this impressive progress.